We have been talking about series, and now we're going to take a step backward and talk more about sequences. This is a very important topic. It's a totally different view of convergence for a sequence. In the usual formulation, we have a sequence converging to some limit that's given. Cauchy's criterion for a sequence is different. It says that as you go farther and farther along in the sequence, the terms of the sequence are getting closer to each other. It's not saying that it gets towards some given limit. But we believe that there should be a limit because the terms of the sequence are getting closer to each other. Now here's the formal statement of Cauchy's condition. We call the Cauchy criterion. A sequence AN is Cauchy if for every positive number epsilon, you'll find that by going far enough out in the sequence, all the remaining terms are within epsilon of each other. Notice we're not just looking at consecutive terms of the sequence to be close. That would not be nearly good enough. What we require is that all the terms beyond some point are within epsilon of each other. If you satisfy this condition, for every positive epsilon, we say that Cauchy's criterion has been satisfied, and then you call the sequence a Cauchy sequence. It's named after Augustin Louis Cauchy, the French mathematician, mostly from the 19th century, late 18th. How does this condition relate to the convergence of a sequence in the usual sense? Because for that, you have to have a limit in mind before you can even talk about convergence. Well, in the real numbers, a sequence converges if and only if it satisfies the Cauchy condition, the Cauchy criterion. So there, in the real numbers, we can regard Cauchy's condition as just an equivalent way of saying that a sequence converges to something. But there's a lot more to be said here. The fact that Cauchy's condition gives an equivalent condition for convergence, it's not true in every setting, it's true in the real numbers, but only because the real number system is complete. In the next video, we'll say more about completeness and the role it plays in the foundations of the real numbers. You should be aware that in the rationals, there are Cauchy sequences that do not converge, meaning that the rational numbers are not complete. Here is a quick example. I've taken a sequence of decimal approximations to the square root of 2. This is a sequence of rational numbers. It's a Cauchy sequence. So if you go past the second term, all the remaining terms are within 0.01 of each other. If you go beyond 10 terms, all the remaining terms are within 10 decimal places of each other. So the sequence of rational numbers is Cauchy. But if your universe, if all you know is the rational numbers, then you have here a Cauchy sequence without a limit. Now there's a process of filling in the gaps between the rationals which gives us the real numbers, where those missing limits can be found. This is the process of completion. And we'll say a little more about that later. At the top of the slide, I'll just remind you of Cauchy's criterion. A sequence AN is Cauchy if for every positive epsilon there exists a capital N, such that if you go beyond n terms in the sequence, all the remaining terms are within epsilon of each other. We just pointed out that this is not necessarily the same thing as saying a sequence converges, but we have at least an implication in one direction. In every case, let's say you're in the rational numbers, the reals, pretty much anywhere, if a sequence converges, then it's Cauchy. So to prove this, suppose a sequence AN converges to L. We need to show that this sequence is Cauchy. The point is that if the terms of the sequence are approaching L, then they must also be getting close to each other. So to prove this, we start as usual by saying let epsilon be positive. By the assumption of convergence, there is a capital N, such that for all little n bigger than capital N, all the remaining terms of the sequence are within epsilon over 2 of the limiting value L. The choice of epsilon over 2 is just a teeny bit of hindsight. If you don't yet see why I chose epsilon over 2, you will in a moment. Because now if m and n are bigger than capital N, the corresponding terms with these indices will lie inside an open interval centered at L with radius epsilon over 2. That's an interval of width epsilon. Any 2 points in this interval have distance less than epsilon. So you can just say that, or you can write it out more formally if you want, if you need to. Let's say that AM is greater than or equal to AN, and if not, then the other way around, and the same idea would then apply. But you would have 2 points sitting inside this interval of width epsilon, as I've said. And if you subtract AM minus AN, then that's less than epsilon. Just follow the previous line, and the inequalities show you this. So similar argument works if AM and AN are in the other order. In either case, the absolute value of AM minus AN is going to be less than epsilon. That's the proof. It's an easy one. Now the converse fails. In general, there are settings, like in the rationals, for example, where Cauchy sequences don't necessarily converge. But at least you can always say that every Cauchy sequence is bounded. It's an easy proof. So let AN be a Cauchy sequence. Then there exists a positive integer, capital N, such that for all indices m and n bigger than capital N, all the remaining terms of the sequence are within 1 of each other. I've used the definition of Cauchy, and I've applied it for a particular case when epsilon is 1. I claim that this number capital M that I'm showing you here, that's going to be an absolute bound for all the terms of our sequence. And I got the first capital N terms covered by what I've included here in my maximum. So that shows that for index little n less than or equal to capital N, that the bound holds. And what about for the remaining terms? For little n bigger than capital N, well then all the terms are within 1 of a sub capital N plus 1. I'll assume capital N is an integer. If it's not, then I could choose a slightly larger integer to make that the case. So we have the absolute value of AN bounded as shown using the triangle inequality. And then I look at the 2 terms on the right side of my triangle inequality. One of them is less than 1. And actually that should be strictly less than. And I get the whole thing is less than or equal to m. So the bound works in all cases. Now, we are ready to show that in the real numbers, every Cauchy sequence converges. So that's saying that the real numbers is complete. We had the converse of this statement before. Convergent sequences are Cauchy. Now we can say in the real numbers, every Cauchy sequence converges. Then in the real numbers, it's an if and only if statement. So let AN be a Cauchy sequence in the real numbers. Let epsilon be positive. If I want to show the sequence converges, what am I going to try to prove? What's it supposed to converge to? Before you can prove that, you have to have a candidate in mind for the limit. You got to have an L. If you want to prove it converges to some number L, what L are you going to choose? So it's a bit of a chicken and the egg problem here. One idea is that by the Bolzano-Weierstrass theorem, we at least have a convergent subsequence. Then we can use the Cauchy criterion to show that this will in fact be the limit for the entire sequence. Before we can do that, however, we need to observe that our sequence is bounded. And that's something we proved just a couple minutes ago. Every Cauchy sequence is bounded. So we can choose a bound M for our sequence. Now, by the Bolzano-Weierstrass theorem, our sequence has a subsequence converging somewhere to a point L. Now that's going to be our candidate for the entire sequence to converge. The point is, beyond some point in the sequence, all the remaining terms of the subsequence are within epsilon over 2 of L, and then all the terms of the sequence are within epsilon over 2 of the subsequence, if you go far enough out. So together, you get the bound for all the terms of the sequence. So let's write that idea down. Our original sequence is Cauchy, so there's a capital N, such that all terms of the sequence with indices bigger than capital N will be within epsilon over 2 of each other. Now let's think a little bit here. How far out in the original sequence do you have to go to make all the terms within epsilon of each other? Well, I need both of the previous inequalities to hold. We'll certainly need k to be bigger than capital K. And for the other part, we need n sub k to be bigger than capital N. The good news is that n sub k is bigger than or equal to k. That's because n sub k is a subsequence of the positive integers. So its kth term is at least as big as k. So for the other part, we need k to be bigger than capital N. So there's two parts to this, and altogether we need k to be bigger than the maximum of capital K and capital N. And then both of the previous epsilon over 2 bounds will hold. And if you put them together by the triangle inequality, then ak, distance to capital L, splits up as a sum of two things, both of which are bounded by epsilon over 2, and the total bound is epsilon. Whenever k is sufficiently large, this bound holds. That's our proof. Now, we just proved one of the key properties of the real number system, the property of completeness. Stated in a different way from before, we have now several results that all depend on completeness, the least upper bound property, the nested interval theorem that requires completeness, the intermediate value theorem, Bolzano-Weierstrass theorem, all of these things, and now the fact that Cauchy sequences converge. These are all different ways of stating the completeness property in the context of the reals. Now in our next video, we want to put together completeness and all the other foundational properties of the real numbers to give the complete and clearest description we can offer what we mean by the real number system. But first, I want to put the Cauchy condition in a more general context. More general than the real numbers, even more general than numbers. Lots of other kind of settings. Anywhere that you have a meaningful notion of distance, you can talk about this property. So let's talk about what is meant by a metric space. That's the general setting where you want to talk about distance. So a metric is a way of measuring distance between points of some set x. And you require that your notion of distance be always giving you a real value greater than or equal to 0. And the distance between 2 points x and y is therefore always greater than or equal to 0, but the only way you get distance 0 is if x equals y. So one of the conditions that you require in order to have a meaningful notion of distance. You also want to assume that the distance from x to y is the same as the distance from y to x. The distance function, in other words, is symmetric. And then you require that the distance function satisfies the triangle inequality. If it does, then you call this d a distance function on the set x. And d is also called a metric. And then x, if it's given this distance function, then it becomes something called a metric space. The Euclidean distance on Rn satisfies these properties, but there are many other examples of distance functions and metric spaces. Even on Rn, there are other ways to measure distance than Euclidean-style distance. In every metric space, we can talk about sequences of points, and we can say what it would mean for a sequence to be bounded. I'm going to leave that one for you as an exercise. Write down what it should be to say that a sequence is bounded. And I'm going to show you as examples, here's what it means for a sequence to converge in a metric space. A sequence of points xn should converge to a point x in a metric space if the following condition holds, namely, for every positive real number epsilon, there's a capital N such that the distance from xn to x is less than epsilon whenever little n is bigger than capital N. So if this holds, you say that the sequence xn converges to x. And you write it using the same notation as before. So for any metric space, you can talk about this property. Now you can also talk about what it means in general to be Cauchy in a metric space, capital X. And you're given a sequence of points, xn. What does it mean to say that the sequence is Cauchy? It says that for every positive real number epsilon, there's a number capital N such that any 2 points in the sequence, both with indices greater than capital N, are going to be at distance less than epsilon apart. So the further out you go in the sequence, the closer and closer the points get to each other. In every metric space, convergent sequences are Cauchy. What about the converse? Well, the converse doesn't hold in general. You say that a metric space is complete if the converse holds. In other words, if every Cauchy sequence converges in that space, of course. Notice that we're talking about the pair xd in parentheses. You wrap them up together, and you call that the metric space, because the point is a metric space is a set with a given distance function. It's not the set by itself that makes something a metric space. It's the set with a given distance function, a given way of measuring distance. This is a question about metric spaces. To be complete is simply the requirement that Cauchy sequences converge. So for example, let's talk about Euclidean distance for a moment. That's not the only notion of distance, it's a familiar one. And Qn, n-tuples of rational numbers, and Rn, n-tuples of real numbers, with Euclidean distance. Here are examples. They are both metric spaces. Rn is complete. Qn is not. Now, one can construct Rn from Qn by a process of completion, which is kind of filling in the space between the points. And the way you do that, the process to complete a metric space, if it's not complete, if you need to complete it, if you need to fill in the gaps, it is by using Cauchy sequences to fill in the gaps. I'll explain the general idea of how this process of completion works. But the point is, this is much more general than just talking about number systems like the real numbers. Because here, Qn and Rn are not actually number systems, they're vector spaces. So let's go back to the rationals and talk about the process of completion. We want to extend the rational numbers to a new number system called the reals. How do we do this? Let's start with an easier question. How do you construct square root of 2? How do you define it to somebody whose universe, all they've ever known is just the rationals? We could use this Cauchy sequence definable in the rational number system. It's a sequence of rational numbers, happens to be Cauchy. Actually, there's a slight problem with this example, because how do you define this using rational numbers? You know how to define it because you're saying, I just chop off the digits of square root of 2. But that's kind of a cart and the horse problem, right? Well, actually, you could. You could define this sequence, but it'd be complicated. Here's, however, a more natural choice to define a sequence of rationals that is again Cauchy, and which could once again be used as a way to come up with square root of 2. So you start with starting value 1, and recursively you apply this iteration. And I've talked about this example before. For somebody whose universe is the rationals, this is a self-contained description of a Cauchy sequence. You can use it to come up with something called root 2. But the real point here is that there's more than one Cauchy sequence of rationals that could come up with this new point called square root of 2. So in order to come up with square root of 2, you can't really say square root of 2 is defined as this Cauchy sequence, because what about this Cauchy sequence? It also gives you presumably the same thing. So you don't want to give millions of different values of square root of 2 coming from the many gobs and gobs of Cauchy sequences that all would work. Instead, you have to have some way of saying these Cauchy sequences are equivalent, they give you the same thing. So you define real numbers as equivalence classes of Cauchy sequences of rationals. In our equivalence relation, the two sequences above, the xn's and the yn's, are equivalent in a sense. They both define the same new number called square root of 2. And the equivalence relation is easy enough to define to somebody whose universe is the rational numbers. You can take your two Cauchy sequences and you can just splice them together, alternate from one sequence and the other, x1, y1, x2, y2, x3, y3, and so on. If you put the two Cauchy sequences together, and if that still gives you a Cauchy sequence, then you say your two Cauchy sequences are equivalent. So, what are real numbers? They are equivalence classes of Cauchy sequences of rationals. This gives a construction of the real numbers as a kind of quotient, starting with the set of Cauchy sequences of rationals, modding out by the equivalence relation. In other words, real numbers are equivalence classes of Cauchy sequences of rationals. This should sound something like our previous construction of rationals from the integers, because there again, we used equivalence classes of not quite integers, but pairs of integers. So we took equivalence classes of those, and that gave us rational numbers. This general way of constructing new things by taking equivalence classes is a way of constructing not just number systems, but it's a process for completing metric spaces. Now in our next video, we'll say more about this and give an overview of the foundations of the real number system.